Let's begin. So what is the big deal? Many people have known Newton's first law since 8th grade or earlier, and if prompted with the first few words, most people could probably recite the law word for word. And what's so terribly difficult about remembering F equals ma? It's pretty straightforward. It seems to be a simple algebraic statement for solving story problems, which we will get to very soon. The big deal, however, is not the ability to recite the first law, nor to use the second law to solve problems, but rather the ability to understand their meaning and to actually believe their implications. Because as I've stated, students have a tough time with this. While most people know what Newton's laws say, many people do not know what they mean or simply do not believe what they mean. They just say, yeah, whatever, I'll remember it for the test, but whatever. Cognitive scientists who study how people learn, have shown that physics students come into physics class with a set of beliefs which they are unwilling or not easily willing to discard, despite evidence to the contrary. These beliefs about motion, known as misconceptions, hinder further learning. The task of overcoming misconceptions involves becoming aware of them, considering alternative conceptions or explanations, making a personal evaluation of two competing ideas, maybe using the law of parsimony, remember that one, Cole? And adopting a new conception that is more reasonable than the previously held misconception. It's really talking about doing science, right? And this sort of idea of doing science and science being attacked has kind of become a thing in the media, right? Did you guys see that over the last weekend there? They had the March for Science. It's online. Scientists and science enthusiasts around the world sort of marching and saying, you know, you have to believe the scientists. After all, who are you going to believe about science if you can't believe the scientists?
Santa Claus.
Say again?
Santa Claus.
Santa Claus.
Who else do you believe?
This process involves self-reflection to ponder your own belief systems, critical thinking to analyze the reasonableness of two competing ideas, that is the law of parsimony, evaluation to select the most reasonable and harmonious model which explains the world of motion. Self-reflection, critical thinking, and evaluation. While this process may seem terribly complicated, it's simply a matter of using your noodle, or in other words, just thinking. Thinking. Well, you got to practice it. It's like lifting weights, man. You got to, work on it. The most common misconception is one which dates back for ages. It is the idea that sustaining motion requires a continued force. And Cole has been warming up my ball for me. Thank you very much. There you go. Awesome. Okay. Me and what's his name there? Married the kicking net. Plays for the Giants.
Odell.
Same thing. I warm up. I do a one-handed catch before the physics class. Okay. So if I toss the ball on the floor, what happens?
It rolls.
Yeah, but eventually it's too bad I ran into the tablecloth.
Stop. It'll eventually stop.
Eventually it will stop. How come?
Friction.
Because objects in motion eventually slow down. That's the rule, right?
No.
No, the rule is what?
They keep going. Unless the opposite force acts against them.
Exactly.
And in this case,
Objects in motion stay in motion unless, that's the part that people forget, unless there is some outside force. And 99.99999, not repeating, percent of the time, there is friction, right? Which is slowing it down.
yeah, I was going to say
So in what condition would you,
See how I bring it all together?
in what condition would you be able to like throw a ball and it just keeps going?
Pretty much space would be the only.
What do you mean pretty much space?
Well, anywhere on Earth there's going to be some air resistance,
Yeah, okay,
right?
but I mean, you can take a rocket in space, blow up your little moon suit, throw a rock, and it would just go forever.
Yeah.
There was a whole example on it.
Well, he said just
There was legit a whole example on it.
yeah, he
Yeah.
said just imagine we were in a place,
Yeah.
imagine you didn't
Yes,
creation, so
but,
assume there's-
okay, going back to Zane's example, think about that. There is no air resistance, but there's still going to be gravity,
So
right?
there you go.
So while it may not slow down, it wouldn't actually go in a straight line because gravity would cause it to.
Would your body still have the gravitational force on
Yeah.
it? Okay.
Yeah.
The ship.
I'm going to get to that eventually about how they're weightless in space. I'll get to that. We'll get to that. Okay, this misconception sticks out its ugly head in a number of different ways and at different times. As you read through the following discussion, give careful attention to your own belief systems. View physics as a system of thinking about the world rather than information that can be dumped into your brain without evaluating its consistency with your own belief systems. In other words, you really need to start thinking about everything I say and say, okay, does that match with what I believe? And Zing's done a good job with that. He's asked about the space thing, right? And said, well, where could there be an actual frictionless place, right? It's good. Eh? A wind tunnel?
Like, you know
Aren't you increasing friction in a wind tunnel?
Well, no, like, you know one of those, like, zero gravity space place? Yeah, like a plane going real fast.
Okay. You mean like,
Or like, you know, like those
One of
things that they have
NASA's
in labs where, like, you just kind of float there?
okay. So, well, let's talk about that. What is going on there, Cole?
Well,
So you're in this big cylinder, and there's a big giant fan down here, right? And it's blowing air up, right?
But then
So,
there's something that pushes you down.
yeah, so you've got gravity pulling you down, and you've got this force, wind force, applied force up, right? And those forces are balanced, and so you just sit there. So no, it's not really frictionless. In fact, it's air resistance that's causing you to do that, right? Yeah. It's kind of the exact opposite of what you're saying, right? Newton's laws declare loudly that a net force, an unbalanced force, causes an acceleration. The acceleration is in the same direction as the net force. Why is there no acceleration here in Cole's example?
Because they're equal.
Because the forces are equal, the net force is zero. To test your own belief system, consider the following question and its answer is seen by clicking the button. You can't click, you've got a piece of paper. Are you infected with the misconception? Okay, so one example. Is everyone on it here?
Yeah.
Awesome. Okay. Two students are discussing their physics homework prior to class, like you guys normally do at lunchtime. They are discussing an object which is being acted upon by two individual forces, both in a vertical direction. Vertical, of course, means up and down. The free body diagram for the particular object is shown on the right. Now, I haven't talked to you about free body diagrams, but that's coming up right away. But you'll understand. During the discussion, analytical, pause for laughter, suggests to know a formula that the object under discussion could be moving. Okay, now listen carefully. Zay, I need you to put that away and listen. Anna says that this object could be moving. Key word is could be. That's two words. Could. In fact, Anna suggests that a friction and air resistance could be ignored because of their negligible size. What does negligible mean? So small that you just don't worry about it. The object could be moving in a horizontal direction. Could be moving. Could be. According to Anna, an object experiencing forces as described at the right could be experiencing a horizontal motion as described below. So she's saying that this object could be moving sideways. Could be. Noah formula objects, arguing that the object could not have any horizontal motion if there are only vertical forces acting on it. He says it can't be going sideways because the only forces are up and down. Noah claims that the object must be at rest, perhaps on a table or floor. After all, says Noah, an object experiencing a balance of forces will be at rest. Who do you agree with? Do you agree with Anna or Noah? I'm singing the Jeopardy song in my head, giving you the appropriate amount of time. Who says Anna is correct? Just a few. Oh, and then there's the looks around to see. Okay. Okay, who says Noah is correct? And one more option, who hasn't voted? Okay, so let's try again. Who says Anna is correct? What does Anna say? She says that it could be moving. Hands up, proud.
But she says, like,
Could be moving. It's okay to be wrong. Could be moving. Who says Noah? Noah says that it must be at rest. Well, now things have changed. Got to be at rest? Where's the answer?
there wasn't actually.
You were on it, right there.
There's no answer. How are we going to know?
That's the answer.
Oh, that's the answer? Remember last winter when you went sledding down the hill and across a level surface at the local park? Of course, we've all been tobogganing. Who's been to Barker Hill? Or not Barker Hill, Durston Hill. Durston Hill. Scary, right? Yeah, I know. It was worse when... It was a lot worse before. Who's been to Barker Hill?
People die.
Not near Sioux. No one's died at Durston
Oh, I
Hill.
guarantee you people died.
Did I tell you the story about Randy Dreger? Did I tell you that story?
No, no, sorry.
Alright, so anyways, let's go back to the question. I apologize for getting you off track. It always happens to me. I gotta stop doing that. Imagine for a moment that there was no friction along the level surface from point B to point C. So from there to there, let's say it's frictionless, right? And that there's no air resistance to impede your motion. How far would your sled travel? Forever. Cole, I'm moving on here now. Okay. So I'm between points B and C. It's frictionless. There's no air resistance. The sled would travel forever. Most students I've talked to quickly answer, the sled would travel forever at a constant speed. Without friction or air resistance to slow it down, the sled would continue in motion at the same speed and in the same direction. Now, look at this picture right here. Gravity is down. Is there a normal force up? I haven't really talked about that yet, but yeah, the forces are balanced. And what is Randy Dreger doing right here? Forever and ever. He's going sideways. How is that any different than that? The answer is it's not. Therefore, the forces acting upon the sled from point B to point C would be the normal force, the snow pushing up the sled, and the gravity force. See the diagram? These forces are balanced, and since the sled is already in motion at point B, that's the key. Already in motion at point B, it will continue in motion with the same speed and direction. So, hang on, Bet. As in the case of the sled, and as in the case of the object that Noah and Anna are discussing, an object can be moving to the right, even if the only forces acting upon the object are vertical forces. Forces do not cause motion. Forces cause accelerations, which are? Exactly, well said. Changes in motion. So what does that mean? It means those of you that picked Anna are right. She said this object could be moving. Remember how I emphasized that? Could be. Could be moving. Guess what? It could also be at rest.
Yeah.
Okay, hang on. I need you to think. Don't worry about that. Think.
Every time the forces are balanced. So because if it wasn't balanced, it would go like
Bingo. Leo got it. Every time the forces are balanced, what does it mean, Leo?
It means every time the forces are balanced.
What? If the forces are balanced, then it could be in rest, or not only moving, no, not accelerating, moving at a constant speed. Okay? When the forces are balanced, it's either at rest or moving at a constant speed. Okay? Forces do not cause motion. Forces cause accelerations, which are changes in motion. And that's the key idea to all of these word problems, really. Okay. Newton's first law of motion declares that a force is not needed to keep an object in motion. Slide a book across the table, watch it slide to rest position. It slows down, it stops. The book in motion on the tabletop does not come to rest position because of the absence of a force. Rather, it is the presence of a force. That force being the force of friction, which brings the book to a rest position. Things don't slow down because you stop pushing them. Things slow down because friction is pushing them. Like brakes or air resistance. In the absence of a force of friction, the book would continue in motion with the same speed and direction forever, or till the end of the tabletop. A force, hang on Leo, let me finish this. A force is not required to keep a moving book in motion, and a force is not required to keep a moving sled in motion, and a force is not required to keep any object, horizontally moving object in motion. Yes, Leo. Okay, so all you gotta do is tell me 1, 2, or 3. An asteroid tumbles through space in a straight line forever. Clearly, N1. Objects in motion stay in motion. N1. Hey, just get that earbud out first. You can laugh. But you and a friend are on ice skates, you push her, and you both move in opposite directions. Clearly, N3. Action, reaction.
And two as well.
Oh yeah? Why is that?
Because big mass, big more.
Oh, so if one of you is larger than the other, right? Then the person with the bigger mass is not going to go as far or as fast. Right. Well done, Leo. You drop your books in the hall while running. Your books slide down the hall until they slow to a stop.
And 1 and 3. And
Why N3?
Because it's coming to a stop because of the reaction from the information.
Okay, so you're saying that as the book slides across the floor, it's applying a force to the floor, and the floor pushes back.
And the air pushes back.
Okay. And you say which one? Was it you or Jeff?
I said N1.
N1.
I think it's N2.
Yeah.
Because you're-
Why N2?
Is that one? Well, trick question. They're all of them because they all affect.
Well, I would agree with Dawson say N2 because the book is clearly a lot smaller than the floor, which is attached to the building, and so it has a greater acceleration than the building, right?
Okay, but like,
building.
you're
Yeah.
running.
So it could be two.
It's your binary.
It could be 2, it could be 3, could be 1. Yeah, absolutely. Objects in motion stay in motion unless acted upon by outside force. It could easily be argued that all 3 coal. All 3.
Just relax.
While making a snowman, you make a really big snowball, you push the ball really hard, but it only accelerates a little. Well, that is clearly 2.
Yeah.
Big mass,
Yeah.
small acceleration. Sorry.
There's the action reaction as well.
So yeah, absolutely. You push, it pushes on you, right? That's true. Yep. Hunters typically get a bruise on their shoulder after firing a shotgun several times. That is an N3, but it could also be
N2.
Yeah, it could be, right? Because the rifle has a bigger mass than the bullet, so it doesn't go back as far, and you have a bigger mass than the rifle, so you don't really go back much at all, right? So yeah, could it be action reaction? Absolutely too, right? Your shoulder exerts a force on the right pinion. Cars driving in the rain can trap water under their tires, but the brakes are applied, the car still won't stop. Well, that would be
I have no idea.
and one, objects in motion. A bad situation. Objects in motion stay in motion. You can't apply that force. The second one?
Yeah.
I guess, okay, because you're applying such a small force, the acceleration is very small, and you don't slow down. Good. Leo's thinking. Friction. Friction's always this is always the hardest one. Friction is usually come up with N3, action, reaction. Friction is the reaction force to just about everything. Right? Okay. Okay. Everyone's... Sure, well, let's talk about it. If everyone in the world ran east at the same time, the world would stop spinning.
This is not Superman.
Okay.
No.
Would you hold the sun? Careful, Todd.
That is not the size of the sun.
That is not the size of the sun. That is not the scale distance either. It's just an example. Okay.
Okay.
All right.
on the other side of the school.
In comparison to the.
Where does the sun? Which direction does the sun rise?
East.
In the east. In the east. Now, does the sun? Literally, I'll just take that from you. Sorry. There's East Canada. Does the sun do this?
Yeah.
The earth does.
If you're in,
Those are the people that the world revolves around.
no.
The earth is the center of the universe.
Unfortunately, yes, there are still some people who believe this.
Hey, if you're from Earth's perspective.
From point of reference, right?
Oh,
Bingo, point of reference, well said, Lee. So, it rises in the east, it looks like this, but what's really happening is, the Earth is going this way, right? Okay, so we're all in agreement that the Earth, there's Canada, right? So, our whole continent is moving towards what we call east, right? Okay, so, we're just spinning like this, everyone on Earth jumps up and starts, yeah, this is pretty tough. Once every 24 hours, right? If everyone on east starts running, which way are we pushing? We're pushing west. So if this is going like this and I'm pushing backward, the Earth will stop spinning, killing us all.
Yeah.
How would that kill us all?
Because the sun.
Oh, well, we'll get to that right away.
The sun would melt.
We'll get to that right away, right? So, 8 the world will stop spinning. So which one of Newton's laws is that? This would be?
Action, reaction.
Yeah, it'd be N3, action, reaction, right? You're pushing on the Earth. Or actually, yeah, you're pushing on the Earth. The Earth pushes on you to run forward, right? Now, here's the next part. If the world stopped spinning, the oceans would spill onto the land, killing us all.
Actually,
Yes.
Actually, on the dark side, they probably just not freeze.
What? Does
Of
the
the
gravity?
moon or the dark side of the Earth?
Wouldn't gravity pull it all in?
Because if you think about it, stop moving.
There is no dark side of the Earth.
There's always gonna be some. There's always gonna be that place in nighttime when you get no peace.
Don't hold it.
I don't want question.
Okay, so anyways, the Earth's going like this, right? What's the water doing?
Going
Also, then the Earth stops.
Oh yeah.
What happened to all the water?
Mr. Bennett.
Just like, for example, if I had a coffee cup full of water and I ran right up a cranny and then I let it go, all the water would, right? I forgot to fill it up.
Oh,
You can get it out.
stay in motion.
The water would keep moving, would it not?
Yeah.
So that would be
If it slows.
N1.
What?
The water's in motion, it stays in motion. Okay, now this isn't on the page, but here's the thinker. Who would be in the most trouble? British Columbia or Newfoundland?
British Columbia.
No.
No, British Columbia. Because the way that's spinning, it would topple out.
Oh yeah,
It's spinning this way,
Actually,
right?
all of Canada would be going.
We stop, the water keeps going this way,
Yep.
so it would go from the water, yeah, we have this huge Pacific Ocean across British Columbia. What would happen to Newfoundland? Well, their water would do
I
what?
was gonna say, they get some way. You just have tide.
Yeah, rolling out.
Yeah, like way more.
How long would it
Where's the water go?
How long would it take for the water to get to Newfoundland?
Who knows?
A while, man. Really, if you got in there, there would be no
Well,
problem.
I would say about the distance that it takes the sun to go from there to there, right? So that would be just speed distance. So, couple hours, say you have a couple hours,
Here's the show.
8:30 in Newfoundland.
Wondering why their water's slowly going away.
That'd be weird.
Watch it.
They just get on a big old fishing boat.
Forever.
Would the water keep going forever and ever? Okay, well, would the water, remember, Newton's law says, that's a great question, objects in motion stay in motion. That's kind of the junior high version of it. What it really is objects will keep moving in a straight line.
Unless, but gravity pulls it in.
Okay, so the question is, would the Earth not spinning cause gravity to stop?
Yeah, that's what I want.
No. Yes. No. No.
I think
Because
You
gravity
think so too?
isn't the force of spinning.
I
Gravity
think-
is the
yeah.
force of like attraction. Yeah.
What would we have to find out to prove or disprove that? Like, how can we figure this out?
When it's spinning, yeah.
We need to stop the world.
What if
We
we
just stop the world. We just stop the world right now.
What if we knew that there was some planet or some heavenly body in space that isn't spinning?
The sun? It's spinning. The sun still rotates.
What's the Pink Floyd album?
Dark side of the moon.
Dark Side of the Moon. Why is it not? Why is the album called? Why is that side of the moon called the Dark
Because
Side?
it's not spinning.
Because it doesn't spin.
Ah. So that's
The moon doesn't spin. Is there gravity on the moon?
Yeah. Very little.
1.6. 1/6 that of Earth, and it's got nothing to do with the spinning. It's got to do with the mass.
Huh.
Okay, so yes, gravity would maintain, which would mean the water would stay at surface level. It wouldn't shoot out
So
from
that's
there.
why
I want to miss it.
That was
Should I miss it?
Yeah, it was super funny, but I mean, it was really.
That's all
Right, so if
That was just trash.
7 billion people on Earth could actually get together, completely impossible. 7 billion people on Earth could actually run each at the same time.
How fast are we talking? You know, how fast are we?
No, regular jog. Could we apply enough force to stop the Earth?
No.
There's no way.
What's that?
Tell me where we are.
Yeah, would we have to be in the same location? No. Would we have to be running at the same speed?
Let's put like 7 billion ants on that globe, and like have them all sit there, and I'm like a piece of cheese over here, and I'll like, they'll stop.
You work on that, What's the mass? What's the mass of the Earth compared to the mass of 7 billion people?
Obviously,
The world is a lot bigger. Like, how many people in Canada? 30 million. How much space is there, like, just in this room between people? There's lots of space, right? There is no way that we are anywhere close to the mass of the Earth. Wouldn't happen. And we couldn't get everyone around at the same time either. Can't even make sure I all the way in. Number 10, last one. A powerful explosion can send small materials flying at very fast speeds.
One.
Really?
That's N2.
Why N2?
I think because the bigger the force, and like
And they're small, right? Big force, right? Here it is here. This is really what Newton's second law boils down to. Big force, little tiny mass is going to give you big acceleration. Newton's second law. Okay, so give me 2 more minutes. 2 more minutes. Free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. Ty, follow along. A free body diagram is a special example of a vector diagram. These diagrams will be used throughout your study of physics. We draw these over and over and over. The size of the arrow in a free body diagram is reflective of the magnitude of the force. In other words, bigger arrows mean bigger forces. Okay? The direction of the arrow reveals the direction in which the force acts. Well, duh. Each force arrow in the diagram is labeled. Labeled. Why am I emphasizing that? Because students don't label on the test and lose marks. Labeled to indicate the type of force. It's customary in a free body diagram to represent the object by a box and to draw the force arrow from the center of the box outward in which the force is acting. One example is shown above right. You always draw them out regardless if it's a push or pull. Okay? The free body diagram above depicts 4 forces acting upon the object. Objects do not always have 4 forces on them. There will be some cases in which the number of forces depicted by a free body diagram will be 1, 2, 3, 4, maybe 5, any number. There is no hard and fast rule about the number of forces which must be drawn in a free body diagram. The only rule for drawing free body diagrams is to depict all the forces which exist for that object in the given situation. Thus, to construct free body diagrams, it's extremely important to know the types of forces, which we've been through. Buoyant force, all those things, remember all that stuff, right? If given a description of a physical situation, begin by using your understanding of the force types to identify which forces are present. Then determine the direction in which each force is acting. Finally, draw a box and add arrows for each existing force in the appropriate direction. Label each force according to this type. Now, I need to give you some labels. Okay? Now, what they've used here, I don't like these. So I want you to just, you can cross them out or you can pencil them beside. Zane, you're still learning here. Put the phone down, man. Mom told me the other night that she doesn't need to talk to you during this period. So I shouldn't see your phone. That's what Mom told me. Okay? So F grav, we're going to call that FW. I call it the weight force. It is your weight due to gravity. FW. It always acts which way, Cole? Straight down. Always. FAP. I'm just going to call that FA. Applied force. FA. All of these are F's, and then the small, the subscript is just the type of force. Yeah. Okay. F norm. We're just going to call that FN. It is called the normal force. Okay? Yes, Cole?
I will ask Ty's question. Why is that W? That W.
Weight force. FW. Had you been listening, you would have heard that. FN, normal force. FA, applied force. Friction. You want to take a guess? Yeah, it's big F for force, little f for friction. FF. So those are sort of the basic ones. There are other ones. You can use the label, Sarah. The label that you use makes most of the time not a whole lot of difference. It's for your own purposes. Okay, I've done enough talking today. You have 11 questions. I'm going to check them tomorrow. Do them now. You can easily get it done in the 10 minutes that's remaining.
So we just
All you do is draw a free body diagram for every one of those. Yep. Yeah. Do you want me to do like the first one or two with you? Okay, fair enough. Book. A book is at rest on a tabletop. Diagram the forces acting on the book. So we draw the book. Now, some people say you shouldn't draw the tabletop because you should only show forces. I'm a bit of a believer of drawing the table, but you might see it without. But regardless, what are the forces acting? Well, books live on Earth, so we've got
Gravity.
weight force, gravity, and the normal force. And are they equal, Leo? Okay, to make them equal, we have to draw the arrows the same length. I'm not going to get my ruler out, but if I look at it and go, they don't look like they're equal, then I'm going to get my ruler out. So if it's within, same kind of thing as vectors, plus or minus 3 millimeters. Okay, make it obvious. Does that get you going, do you think? Okay, give her. If you can't get a couple, that's fine. Do as many as you can. Go. Okay, so we did the first one, right? Weight force, normal force, arrows should be balanced. Ty, stay with me here. A girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. Diagram the forces acting on the girl. So you don't have to be an artist. You can just draw the girl as a box like that, just a rectangle, no big deal. Right? It's happening on Earth. Ty, stay with me. It's happening on Earth, so we've got gravity, FW. Okay. Weight force, that's her weight, the weight due to gravity, FW. It's the bars hanging from the ceiling by 2 ropes. Diagram the force acting on the girl. So now there's really 2 forces up, right? 2 ropes, 2 arms, right? We could call those, now here's where the confusion is. You could call them both FA. Maybe you need to call them FA1 and FA2. Some people prefer to call them FT, F tension. It's okay. It doesn't matter what the labels are. I know that some of you are going to get hung up on that. Okay? What matters is what forces we're talking about here. AJ, you need to get that earbud out again. Okay? Now, having said all of that, these 2 arrows should do what? Oops, they should be... These 2 arrows should do what? They should equal the length. Now, I've got a problem. My forces are not balanced, which means what's going to happen to this poor girl? Why? She's going to accelerate upwards, right? So this force needs to be, this force needs to be as long as those 2 combine. Okay? Should sort of be more like that. Does that help? It's okay if you don't get this right away. That's the only one? Okay, well let's do 3 and 4 because I know they're all on the front page. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the force acting on the egg as it falls. So here's the egg. It's kind of square. It's falling from a nest in a tree on Earth.
All the way down.
Gravity, down. It says neglect air resistance. Anything else? That's it.
He's going down quickly.
No different than anything falling, right? Yeah. A flying squirrel is gliding. Now that is a code word for constant velocity, not accelerating. Gliding means constant velocity. It's the last one, you guys. From a tree to the ground at constant velocity. Consider air resistance. Diagram the forces acting on the squirrel. So here's the squirrel. Again, gravity. down. Gliding means constant velocity. Constant velocity means no acceleration. No acceleration means that the forces are equal or balanced, and so my air resistance, I'll call it FAIR, air resistance. Or I guess if you want, it's really a form of friction, right? Again, I don't want you to get hung up on the labels. I know some people get frustrated by that because they don't know what to call it, right? Take a guess. It's okay. Try. Okay? But the key here is that these forces are going to be equal. Okay. Does that help you out with numbers 5 to 11? Okay. Giver. I'm going to check those tomorrow.